So in our previous lecture we talked about the Taylor series, and today we are going to talk about yet another power series which we call the Laurent series. Okay, so to begin with we are going to state the theorem which gives us the conditions and the conclusion of the Laurent series. Okay, and like we have ready-made formulas to find the coefficients of the Taylor series, we also have ready-made formulas for the coefficients of Laurent series. Okay, so I will tell you what the bad news about the coefficients is and the good news is. Okay, as when we see the series in detail. Okay, and it actually turns out that we seldom find the values of the coefficients by the formulas. Okay, so there are better ways to find the coefficients of the Laurent series, and these ways can be rearranging the terms given in the function's definition, or you can use the Taylor series expansion of the constituent functions, one or more. You can also use the substitution method to use Taylor's series. For example, if you have sine of sine z, so in this case you can use the expansion of sine to get the expansion of sine z. Okay, so basically you substitute for the inner variable as well, you substitute for the inner function as t. Okay, and then again you use the Taylor or Maclaurin series. Okay, and quite often you're also required to make use of partial fractions. Now this is true when you have a rational function. Okay, and you are also required to use geometric series here. Okay, and remember in our previous lecture we saw the geometric series, right? And we saw the two modifications which were required for the convergence. Okay, now these were for 1 upon z minus z naught. If you take z common and if you take z naught common, then you get two different expansions, okay, which have different radii of convergence and hence different regions of convergence. Okay, so we will see that through an example, one each corresponding to all four methods. Let us start discussing the Laurent series. Okay, so the theorem says the following. Suppose we have an analytic function f of z. Okay, and the region on which it is analytic is this annular region A. Okay, the center of the annulus is the complex number z naught. Okay, and the outer boundary is given by the radius r2 and the inner boundary is given by the radius r1, but note that this is an open region. Okay, meaning it doesn't have any boundary. Okay, if it had boundaries then we would have put the signs of less than or equal to. Okay, so suppose f of z is analytic on the annular region A, then the conclusion of the theorem says we can actually express f of z as a series. Okay, now conventionally the Laurent series is said to consist of two parts. Okay, part 1 is known as the principal part or singular part, so these two words are used interchangeably, and the second part is known as the regular part or analytic part. Okay, now first let us talk about the regular or analytic part. This part of the Laurent series consists of non-zero integral powers of z minus z naught. Okay, so this is what we were calling a power series. N can take values from 0, 1, 2 till infinity, an times z minus z naught to the power n. Okay, and z naught is obviously the center of the annulus and also the center of the Laurent series. Okay, then comes the next part. Okay, that is the principal part or singular part. Okay, now this part consists of terms which have negative integral powers of z minus z naught, and as you can see here, z minus z naught is in the denominator and raised to n. Okay, so the principal or singular part consists of negative integral powers, and regular or analytic part consists of positive integral powers as well as the constant term. Okay, so this is the theorem. Okay, and the series that we get is known as the Laurent series. Now, just like we have formulas for coefficients of a Taylor series, okay, we also have formulas for coefficients of Laurent series. Okay, now deliberately we have called the regular the coefficients of the regular part as an, okay, and the coefficients of the principal or singular part as bn. Okay, now let us read out them. Bn is defined as 1 upon 2 pi I times the integral of f of omega into omega minus z naught to the power n minus 1 d omega. So here omega is the variable of integration, and gamma is any closed curve, or I would say any simple closed curve which belongs to the annular region A, which you can see here in the blue color. Okay, note that C1 and C2 are not parts of the annular region. Okay, only the interior is the annulus. Okay, and you can see the black curve gamma, which is not necessarily centered at z naught. Okay, so you can take any such any simple closed curve. Okay, so that is bn, and for an we have 1 upon 2 pi I into the integral of f of omega upon omega minus z naught to the power n plus 1 d omega. Okay, any circle z minus z naught equal to r, omega minus z naught equal to r inside the annulus, and well, it need not be centered at z naught, it can be centered anywhere. Okay, now what I want you to notice is the principal part's coefficient when n is equal to 1. That means the coefficient of one upon z minus z naught. Okay, if you substitute n equal to 1 on the in the integrand, then we are going to get b1 as 1 over 2 pi I times the integral along gamma of f of omega d omega. Yes, now the result is interesting, because if by some other means we manage to generate the Laurent series of any given analytic function satisfying these requirements, then we have actually computed the value of this integral. Okay, this integral's value will be 2 pi I times b1. Okay, this is actually called as the residue. We will talk about it later, but what I wanted you to note is if we let n to be 1, then we can actually get the value of the definite integral along a closed curve inside the annulus A. Okay, that is only for b1. The second thing that you should remember is the difference between the principal or singular part and the regular or analytic part. Okay, principal part means negative integral powers of z minus z naught, where z naught is the center, and regular or analytic part means either the 0th power or positive integral powers of z minus z naught. Okay, one more thing is f of z need not be defined at z naught. Now this is something different from Taylor series. Okay, the first difference is in Taylor series we do not allow the negative integral powers, and the second thing is not only the function but also all of its derivatives should be defined at the center of the Taylor series. Okay, that is what the formula says or the theorem says. However, for Laurent series, when you are expanding the function f of z, okay, as per the theorem, inside the circle mod of z minus z naught less than r1, the function need not be defined at all, but still you can get a Laurent series about that particular center. Okay, so this is yet another difference between the Laurent series and the Taylor series. Okay, now let me tell you the bad news first and then the good news. Okay, the bad news is that the coefficients or the formulas that are there to find the coefficients, they are not as easy as, well, the formulas for Taylor coefficients. The only reason is these involve integration. Okay, so no formulas available for the coefficients in terms of derivatives, simply because the requirement of differentiability is not there for f of z, okay, at the center. Okay, although we assume that it is analytic, we don't assume the analyticity of the function at the center. Okay, so and we also know that derivatives are always easier to obtain compared to integrals. Okay, so that's the bad news, but the good news is that we seldom use these formulas to actually get an and bn. Okay, as far as the Laurent series expansion is concerned, we always have other ways to obtain them, and thereby we can actually get the values of these integrals as well. Okay, fine. So we will focus more on the good news. Obviously, we will see now that there exist a lot of ways to actually generate the Laurent series of any given function, and we will solve problems corresponding to each of the methods. Okay, there are 4 of them which I will be covering, but there may be a combination of them which may be required to be applied in the problems. Okay, so let us now see the ways to generate the Laurent series of given functions. Okay, yes, so as I said, we will be talking about 4 different methods to get the coefficients of the Laurent series. Okay, and in particular we will be talking about these 4 functions. Okay, the first one is z plus 1 upon z, a rational function. Second, z to the power minus 5 into sine of z, product of, well, a rational function and a trigonometric function. Third, z cube times the composite exponential function where the exponent is 1 upon z, and the fourth one is z upon z squared plus 1. Okay, now you may see that except for the fourth, all other functions are not defined at 0. Okay, simply because you have 0 in z in the denominator, okay, or a power of z. Whereas the example 4 consists of a rational function which is not defined as defined at z equal to plus or minus I. Okay, so we will actually be interested in generating the Laurent series, okay, about these particular points where the functions are not defined. Okay, so let us see all these methods one by one. We will start by rearrangement of the terms in the function. Method number 1. Okay, the question is, find the Laurent series for f of z equal to z plus 1 upon z around z naught equal to 0, give the region where it is valid, so basically the region of convergence, and also we have to identify the singular part or the principal part. Okay, now let me remind you that the singular or the principal part is that part of the expansion or of the series which consists of negative integral powers of the term z minus z naught. Okay, fine. Alright, now see, by rearranging, I mean if you split the numerator, you will directly get the terms z plus 1 upon z. Okay, now because we are expanding, or we are expected to expand it around z equal to z naught, we may now write this as z minus 0 plus z minus 0 to the power minus 1. Okay, so the Laurent expansion or the Laurent series of the given function consists of only two terms. Okay, and the coefficients of both these terms are 1. So in usual notations, a1 will be equal to 1. Okay, and b1 is also equal to 1, isn't it? And there is no need to write the other terms because all the coefficients are equal to 0. So there is no constant term as well in the expansion of this particular function. Okay, now let us talk about the region of convergence. Now as far as the original function is concerned, it is a rational function. Yes, and we have seen that rational functions are analytic everywhere except for those points where the function's denominator is equal to 0. Okay, therefore the region of convergence of the Laurent series will be the entire complex plane excluding the number 0. The other way to put it is 0 less than mod z less than infinity. Okay, now let us talk about the singular part and the analytic part. Okay, singular is also termed as principal, and analytic is also termed as regular. So the analytic part consists of the constant term and the positive integral powers. So z is the analytic part and the remaining is 1 upon z, so that is the singular part or the principal part. Okay, so now we have answered all three. We have found out the Laurent series by rearrangement of the terms. We have we have come up with the region of convergence or the region of validity, and we have identified both the parts. Okay, I mean, once you identify the first part, the rest is very easy to obtain. Okay, just remove those terms. Okay, now this example is telling you that you can have a non-polynomial function, okay, with finitely many terms in its Laurent series expansion. Okay, because it is a rational function, it has only two terms in the Laurent's expansion. So this was the first one. We have covered z plus 1 upon z. Let's now go to the second one. Okay, that is, we will now make use of the Taylor series expansion of the functions. Okay, method 2, using Taylor's series or Maclaurin series. The question is, find the Laurent expansion of z to the power minus 5 into sin z about 0. So here z naught is equal to 0. And we will also do the process of finding the regular part and the principal part. Okay, fine. So here you observe that we can bring in the Maclaurin series of sin z because the center is 0. Okay, so let's do that. Keep the first term as it is, that is, keep z to the power minus 5 as it is, and bring in the Maclaurin's expansion of sin z, which is z minus z cubed upon 3 factorial plus z to the power 5 upon 5 factorial, and let us write down two more terms. Okay, because the largest power here in the denominator is 5. Okay, so writing down the third term will only give us the first term of the analytic part, so let us write down two more. And because calculators are allowed, finding factorials should not be a big problem. Okay, fine. So see, by doing this, we already know that sin z is analytic everywhere, so it must have a convergent power series. Okay, in a neighborhood of 0, deleted neighborhood. So let's now multiply term by term. Okay, when you multiply z by 1 upon z to the power 5, you are getting 1 over z to the power 4. If you do that with the second term, you are going to get 1 upon z squared into minus 1 upon 3 factorial. Okay, now note that if you multiply the next term by z to the power 5, you are going to get the constant term, and then onwards you'll go on getting positive integral powers of z. Okay, which means in the Laurent series expansion of the given function, that is sin z upon z to the power 5, the singular part or the principal part consists of only two terms. Okay, those two terms are 1 upon z to the power 4, hence b4 is equal to 1, and negative 1 upon 6 into 1 over z squared. So b2 is negative 1 upon 6. All other bn's are equal to 0. Okay, so this is b1, this is b2, this is b3, which is 0, and b4 is 1, and all other terms are 0. Okay, for all values of z. Now obviously the remaining part will be the analytic part. Yes. Okay, so b1, sorry, not b1, a0 is 120, and this being now an even function, so to speak, it will not have any odd power of z. Okay, so a0 is 1 upon 120, which is 5 factorial. Then we'll have a2, which will have a negative sign, negative 1 upon 7 factorial, which is 5040, and then a3 will be 0, and a4 will be positive 1 upon 9 factorial. Okay, and so on. Now, having identified the principal part and the analytic part, let's also talk about the region of convergence. Okay, and like the previous problem, this particular function is a ratio of two analytic functions, sin z upon z to the power 5, and z to the power 5 is not defined only at 0, it is analytic everywhere else. Okay, because it is a polynomial function, right? So again, the validity or the region of validity will be the entire complex plane without the complex number z equal to 0. Okay, so we can make use of the Taylor series or the Maclaurin series directly, provided we ensure the convergence of the series. Okay, so this is the second way to obtain the Laurent series. Let's now go to the third one. We have now completed this. Let's now make use of the substitution, essentially a subtype of the Taylor expansion. Okay, type 3, by substitution. Find the Laurent expansion of z to the power 3 into e to the power 1 over z about 0. So again, the center of the Laurent series is 0. Okay, fine. So what we can now do is we can let 1 upon z to be t and bring in the Maclaurin series of e to the power t, 1 plus t squared by 2 factorial and so on. Okay, and we have to now replace t by 1 over z, and then we have to multiply it by z cube. Okay, the first function. So this is what I've done. This is 1 plus t squared by 2 factorial, the third term, then t cube by 3 factorial, and so on. Okay, t to the power 4 upon 4 factorial. Okay, so then what you do is you multiply each and every term of the bracket by z cube. So it is z cubed into 1, so z cube plus z squared plus z by 2 plus 1 over 6, and see, after this you'll go on getting powers of z which are negative. Okay, if we were to write the next term, it is going to be 1 over 120 into 1 upon z squared. All right, which is basically t to the power 5 upon 5 factorial, and you have z cube here, which means in this case the analytic part is a finite series, okay, which consists of a naught as 1 over 6, a1 as 1 upon 2, a2 and a3 equal to 1. Okay, whereas the principal part is the singular part is an infinite series. Okay, 1 upon 24 into 1 upon z plus 1 upon 120 into 1 upon z squared, and so on. Okay, so no bn is 0 here. All bn's are non-zero. Now this has something to do with the singularities of the function, which we are going to talk about later. Okay, so you can actually write it down using the summation notation as the principal part is equal to summation 1 over n plus 3 factorial into z to the power n as n runs from 1 to infinity. Okay, and this is enough to establish the fact that for this there are infinitely many terms in the principal part, but only finitely many terms in the analytic part. Okay, what was the situation here? Here the analytic part consisted of infinitely many terms and the principal part consisted of only 2 terms. Okay, and in the first example both consisted of finitely many terms, in fact only 1 term each. Okay, so we have now completed the third substitution. Let us now talk about the method of partial fractions. Okay, now this is a bit complicated because of the regions of convergence. Okay, so let us now try to find out the Laurent series of z upon z squared plus 1, okay, using the partial fractions. Okay, method for using the partial fractions. The question is, find the Laurent series for f of z, which is z upon z squared plus 1 around z not equal to I. Okay, so this is one of the points where the function is not defined, and we are going to call those points to be singularities. Okay, give the region where it is valid and identify the singular or principal part. Okay, so a similar problem statement, only difference is this time the center isn't 0 and the function is a different function. Okay, fine. Now first thing to be understood is if we want to expand it around z not equal to I, it implies that we must have the powers of z minus I in our expansion. Okay, step 1, use partial fractions the way we do it in integration. Okay, now because these consist of 2 linear non-repeated factors, okay, the split is going to be a upon z plus I plus b upon z minus I. Yes, and it's not very difficult to get the values of a and b. Both will turn out to be 1 upon 2. Okay, well, this is b, z minus I, and this is a. Okay, the shortcut is to equate the denominator to 0. So if you equate z minus I as 0, you have to then put the solution of that in the remaining part. Okay, so if z minus I is 0, then z will be equal to I. Put it in the remaining expression. So it will give you I upon 2I or 1 upon 2. Now for z plus I equal to 0, z is minus I. So minus I upon minus 2I, I and minus sign will go. So again you will get 1 upon 2. Okay, you can always cross check it by cross multiplying. Okay, now Because the center that we want is z minus I, we should not touch this particular part, okay, because it already has the negative 1th power or negative first power of z minus I. Okay, what we should now look for is this particular term 1 upon z plus I, and this very much looks like the term a upon 1 minus r, isn't it? Yes, and also it is not in terms of the powers of z minus I. Okay, so the obvious way would be to first write it in terms of z minus I and see what happens. Okay, so add and subtract I, or subtract and add, so it will be z minus I plus 2I. Okay, till this part everything is okay, but from now on we will be solving two problems, meaning we will be finding two different Laurent series which are valid in two different regions of the complex plane. Okay, first what I will do is I will take 2I common from the denominator of the second term. Okay, so this part is not going to change or has not changed, as you can see. Okay, and even this 1 upon 2, it will get incorporated with 2I and it will become 4I. So if you take 2I common here, okay, it will become 4I. Yes. Now what will happen inside? After taking 2I common, this will become 1 and z minus I will become z minus I upon 2I. Okay, and also we would like it to be in this form, 1 minus something in the denominator, so change the sign of 2I. Okay, and this is exactly acting like the common ratio r. Okay, so 1 upon 1 minus r, what is the associated geometric series? 1 plus r squared plus r cubed and so on, and this series represents the term 1 upon 1 minus r only when mod r is less than 1. Okay, fine, so we actually can get it in the powers of z minus I now. That was our main objective. So it is 1 upon 2 into 1 upon z minus I plus 1 upon 4I into 1 plus r squared and so on. Okay, so 1 plus z minus I upon minus 2I, this is r, plus z minus I upon minus 2I to the power 2, this is r squared and so on. So we have achieved our objective. We had to obtain the Laurent series of z upon z squared plus 1. Okay, and let us now write down the validity, the region of validity of the expansion. Okay, the validity condition is mod of r has to be less than 1, or the absolute value of the fraction z minus I upon minus 2I has to be less than 1. Using the properties of the modulus function, we can say that mod of z minus I has to be less than 2, because mod of minus 2I is 2. Okay, and well, yes, because you cannot now have z equal to I because of this principal part. The region of convergence will be 0 less than mod of z minus I less than 2. Okay, alright. Now, is it possible to identify the principal part and the analytic part? Yes, this is the analytic part. A naught is going to be 1 over 4I. A1 is going to be minus 8 into I squared, so 8 in the denominator, so 1 upon 8 and so on. Okay, so these are the coefficients A0, A1 and so on, and we only have B1 here. B1 is 1 upon 2 and everything else is going to be 0. Okay, so this particular expansion is valid only when the absolute value of z minus I lies between 0 and 2. Okay, now let us go back to this term. Okay, let me show it in green color, this term, and try to take z minus I common from the denominator. Okay, let us see if that comes up with a different result. Okay, so if you take z minus I outside, what will we get? We will get the following. It will be now 1 upon, this will be 1 plus 2i divided by z minus I. Okay, and again we would like it to be in the form a upon 1 minus r. So change the sign of 2i. So this time this is our r. Okay, all right. So now you can use the formula yet again, 1 plus r squared and so on, provided mod r is again less than 1. Okay, so 1 plus r minus 2i upon z minus I plus r squared minus 2i upon z minus I squared and so on. Okay, and don't forget that because we have taken z minus I common from the denominator, everywhere this factor is going to be there. Okay, so it is 1 upon z minus I into 1 first term plus minus 2i upon z minus I squared and so on. Okay, so all these terms have negative integral powers of z minus I. Okay, and let us not forget that this has 1 upon 2 as its coefficient, and we also have an additional 1 upon 2 times z minus I. Okay, so if we were to write the Laurent series expansion of f of z for this particular region of convergence, it will be 1 upon 2 times 1 upon z minus I plus 1 upon 2 times the series that we have got here. Okay, 1 upon z minus I plus minus 2i upon z minus I squared plus minus 2i upon z minus I cubed and so on. Okay, so let us now simplify this and then let's talk about the convergence. Okay, all you have to do is add these two terms. So 1 upon 2 into 1 upon z minus I plus 1 upon 2 into 1 upon z minus I will be just 1 upon z minus I. So b1 is going to be 1, b2 will be negative I, b3 will be let's not forget this too. So b3 is going to be 2 in the denominator, square of minus 2 4, square of I minus 1, so b3 will be negative 2 and so on. Okay, so again you observe that this particular function, okay, is represented by a Laurent series which doesn't have the analytic part at all. Okay, everything here consists of only the negative integral powers of z minus I. Okay, now let's talk about the validity of expansion. Okay, remember we are now considering the common ratio to be minus 2i upon z minus I, and for the validity of the expansion the absolute value has to be less than 1. Yes. Okay, which means this expansion is valid for all those complex numbers for which mod of z minus I is greater than 2. Okay, I mean you have to take this to the other side and do the necessary calculations. Okay, so mod of z minus I is greater than 2. This is a different region of convergence obviously than this. Okay, in fact both are complementary, you can say, or at least you can say that their intersection is a null set obviously. Okay, which means the Laurent series of the same function can be different in different regions of convergence. Okay, for the first one we got a series consisting of only single term in the principal part or singular part and all other terms were in the regular or analytic part. Okay, all the positive powers of z minus I as well as the constant term. Okay, whereas for the other region of convergence, okay, what we have got is now no regular or analytic part. Okay, because there are no powers, positive integral powers of z minus I and the constant term. We only have got the negative integral powers of z minus I. Therefore a function may have different Laurent series in different regions of convergence. This part is important, okay, in different regions of convergence. Quite often people tend to believe that within the same region of convergence a function has different Laurent series. That is not true. For a particular region of convergence, if at all the series converges, it has to have a unique Laurent series representation. So you cannot have two different Laurent series for the same ROC. Okay, it may have different Laurent series in different regions of convergence, and the example is right in front of us. Okay, we have used partial fractions, and we have made use of the geometric series which we talked about in our previous sessions. Okay, so these are the four methods to find the coefficients or to generate the Laurent series, and in all four of them we haven't used this formula, okay, for Bn as well as for An. I mean, in some of them we have used the Maclaurin series, of course, and that's the good news. Okay, there are easier ways to compute the Laurent series, so yeah, there is no need to perform the integrations. In fact, we are actually going to calculate those integrals by the residue integration method by evaluating the Laurent series and calculating B1, as I told you right at the beginning. Okay, if we let n to be 1, it is just the integral of f of omega d omega, because this term then becomes 1. Okay, because it is, oh okay, yeah, okay, so it is 0th power, n is also 1, so 0th power, so it becomes 1, so the integrand is just f of omega. Okay, all right. So as far as the Laurent series is concerned, this is it.